Hello. In this video, we're gonna solve the wave equation and on unbounded domains. Okay. This means we're gonna solve it on the whole real line. Okay. So there is a very nice formula. So let's call it proposition. Proposition. So the wave equation and this looks like second derivative with respect to time equals to c squared times the second derivative with respect to x, and you have ux0 equals f of x, and then you have let me put it here, ux0 equals f of x, and then utx0 equals g of x. So this system has the Allenberg's formula. So we're going to prove the Allenberg's formula. The Allenberg formula. I'm sure this has a right pronunciation in French that I don't know. That has the Allenberg's formula solution. So it looks like this. So uxt equals 1/2 f of x plus ct plus f of x minus ct plus 1/2c integral of x minus c t x plus ct g of y dy. Okay, so what is this formula so celebrated? So let's make an example before getting. We're gonna get on all these details. So let's make a good example so I can sell you this formula. So let's consider just the same we said, this one, and then let's say ux0 is something we know, like e to the minus x squared. Okay, and let's say utx0 is 0. So when g is 0, this I don't have this last term, right? So what my formula is saying is that my solution, the solution by the Allenberg's formula is uxt equals 1/2 of f of x minus ct. So what is f? So f is this guy. Okay, f, you see it? F is that guy. So it's 1/2 of e to the minus x plus ct squared plus e to the minus x minus ct squared. Okay, why is this a good formula? Because we know how is e to the minus x squared. Maybe you don't remember, but that's the Gaussian formula. That's what statisticians love, and they call it normal distribution. Okay, so let's say this usually this is e to the x minus e to the minus x squared. Okay, so so people love those, but what it's saying here, so let's erase this line. What it's saying here is that this is e to the minus x squared, okay? But this term is telling me that this is a wave moving to the right. right? Because minus is saying is moving to the right. It's a shift, right? On time, well, the velocity is c. So for each minute, or let's say my units are minutes or hours or whatever you want. So for every hour, I have moved c units to the right. So this wave is moving this direction, and it's called, I'm gonna call it e to the minus x minus ct squared. And the other one, this one, is called, let's call it, let's make another call. I'm gonna call it e to the minus x plus ct squared. So this one is moving to the left. I'm sorry, this is moving to the right. This guy is moving to the right. The other one is moving to the left. Okay. I think I said it wrong. Okay, so what happens? So this is a wave and this is another wave. So I have wave 1 and wave 2, right? So what happens when t equals 0? When t equals 0, what happens? They overlap. So when t equals 0, they make a new wave. Let's say t0 is here. So this, they're supposed to be the same way. So I apologize. These waves don't look very similar. Let me erase this one. Let me try to make it better. At least as bad as the other one. A little bit better. So there's exactly the same wave, okay? And when t equals 0, so you see this one has 1, 2, 2.5. They're 2.5 tall, 3.5 tall, okay? So when they overlap, they must have 7 tall. So 1, 2, 3, 4, 5, 6, 7. So at 7 they overlap, and this is my wave. Oh, sorry, it has to go down. Okay, so this is t equals 0. Okay, so you could, for example, you could say, we could say, pretend that we will say t equals 1. So this will be 1, and this will be 1. At t equals 0, the has, and at t equals, let's say t equals 2. What happens at t equals 2? At t equals 2, they just move, the green one moves to the position where the to the other side, and the green and the orange move to the other side. So basically I have something similar that I had before. And that's what is called wave equation, because it simulates this behavior. So my color on the, so now I'm gonna have green color on the right. So I'm gonna have green color here, and now my orange is gonna be in the other side. Okay, this is at time 2. So basically, two waves are coming. They, by superposition principle, they overlap. They survive the superposition, and then they keep moving. This is moving to this way, and this is moving to that side. So you see, this is very cool, because this this theorem is allowing me to make sense of this model, okay? And deserves the name wave equation. Okay, so let's go to the proof. So for the proof, we're gonna do as the same technique we have been using, and you will be doing the same for your homework. So let me try to illustrate what I mean. So I'm gonna okay, here I'm gonna fill it up here. So I knew I have it somewhere. So the proof gonna go like this. Okay, so this means my sketch of the proof, because it's gonna be long, and there's gonna be a point you probably have to see it started today and continues tomorrow, because probably you're gonna feel tired. Okay, so we take the wave equation. We have ux0 equals f of x, and utx0 equals g of x. Okay, so this you have to. I expect you to do it this way when you are solving your homework, so you know what you are doing. Okay, otherwise it's gonna be really messy. You're gonna forget what you're doing. So we're gonna take the Fourier transform. Okay, and then over here we're going to transform this partial differential equation in an ordinary differential equation that we're going to call second derivative ukt with respect to time equals minus c squared k squared ukt, and then we have uk0 equals f of k, and then we have derivative of uk0 divided with respect to time, and this is gk. Okay, now you solve this using your ordinary differential equations. And then you obtain the following. You obtain UKT equals FK divided by 2 e to the ICKT plus e to the minus ICKT plus G of K over 2ICK, and then you get e to the ICKT plus e to the minus ICKT. Okay, so now when you go back here with Fourier transform inverse, you're gonna get here, you're gonna get the Allenberg's formula. Okay, so let's see how much time has my video, because sometimes it's 13 minutes. So yeah, I'm gonna do, and don't like to make videos more than 30 minutes, because then it's a problem to, sometimes it's a problem to upload them later. I don't know why, but some videos lose their audio or something like that. Okay, so let's start. So let's start with the proof. So proof, this is the proof. So we're gonna start, let's start taking the Fourier transform to the problem. So what does it mean? So I had to take the Fourier transform to UTT, u second derivative with respect to time of u equals c squared u xx. So let's just go step by step. So the Fourier transform of second derivative with respect to time by formula we saw in a previous video. This is just the second derivative with respect to time of the Fourier transform of u. So let me make a big U. So this is a small u, and this is the Fourier transform of u. Then I use u, capital U, and then use kt. So I like this notation. I'm following Debnav's book. Okay, Debnav's. Sorry, my battery. So Debnav's book. Okay. So then I take the Fourier transform of the second derivative with respect to x of u, and then again for the formulas we saw before, this is minus c squared k squared u kt. Okay, those are formulas. Now the Fourier transform of small u x0, so I know that's the Fourier transform of f of x, right? So this is, by definition, this is the capital F of k, following the notation. So k is my variable for the Fourier transform. Before I had used zeta, right? Basically, I kind of, depending on the book I'm using the notation, just to, to avoid dilemma if there is a mistake or something, and just easier to find. And you just need to get used to see. You can say k, you can see for Fourier transform variable, you can see k, you can see zeta, you can see omega. Okay, so you just get used to it. Okay. And then the Fourier transform of utx0, with respect to time, and Fourier transform here of g of x is capital G of k. Okay. Okay, so so when we plug in this thing together, so ut equals c squared uxx, right? So we can put, oh, sorry, here I should put c squared. Is that c squared or no? Let me see. C squared, yeah. I put c squared, so let's keep putting c squared. Sometimes people put c. Okay, so, and then I take the Fourier transform of the initial data. Ux0 is capital F of k, and then Fourier transform of the last one is gk. So you see, that's my first step. I'm obtaining this system. So I have derivative, second derivative with respect to time. So this is ordinary differentiation. Okay. Ukt equals minus c squared k squared ukt, and then you get so you see this one becomes capital U k0. Okay, and this one by properties becomes derivative with respect to time of capital U k0. So I obtain capital U k0 equals f of k, and then here obtain derivative with respect to time of capital U k0 equals g of k. So I have obtained my first step. Okay, so this is this step. Now the next step is to solve using my ordinary differential equations. But you see, this might look scary for you. Oh no, maybe not. But this is just a normal differential equation. You have solved this many times. So let me put it in more familiar terms. So this one is just, let's say, instead of u, let's say y. So this is second y prime, right? Equals minus c squared k squared y. and forget about the k. The k is just a number. So you just put y0 equals f of k, and f of k is a number, and y prime 0 equals gk. Okay. So this is just what we need to solve. Okay. But we're more familiar with this, right? Because we know how to solve this one. Because we have done it many times. So, so in particular, you move it to this side. You got 0, and please don't use Laplace transform to solve something like this. Laplace transform is for non-homogeneous when you have something g of t here. Okay, this is too easy to use Laplace transform. So just use our characteristic polynomial. So this using characteristic polynomial, you get m squared plus c m squared plus c squared k squared equals to 0, and then this changes to m squared equals minus c squared k squared, and then this becomes m equals plus minus ick. Okay, so usually when we write complex, when this m is complex, we write the form in the in another way. But this time we want gonna do it. We're gonna write the solution with these values we found. So the solution is gonna be y of t, just because it's easier. Okay. So what is next is gonna be easier. C1 e to the ICKT plus C2 e to the minus ICKT. So for engineers, physicists, they prefer to work with in mathematicians also. They prefer to work with e to the ICKT, that cosine of CKT plus ICKT, because it's too complicated to apply Euler formula. So this is, you're gonna see how nice everything simplifies. Okay, so this is my solution, but I have y0 equals f of k. That means I need to plug in at 0 this, so I got, when I plug in t0, I get c1 plus c2. Okay, and when I need to find y prime, so next one is y prime 0 equals gk. So I need to find y prime of t. So y prime of t, you just find the derivative of this. This is chain rule. So that's the e to the ICKT times the derivative of the inside, so it will be C1's ICK. And this will be plus C2 times minus ICK e to the minus ICKT. Okay. So then you have to plug in at 0. When you plug in at 0, y prime of 0, you get, this guy is gone, so you get C1 ICK minus C2 ICK equals to g of k. So we have to solve that system. We need to find what is C1, C2. We need to find what is C1, C2, C1, C2. And the system is, so we need to solve the following system. We need to solve the following system. And this is C1 plus C2 equals f of k, and the other one is I oh no, you wanna call let's call it like this. ICK C1 plus minus uh, ICK C2 equals G of K. Okay, okay. So we need to solve this system. So even if it's complex, well, we just solve it the usual way we solve it. So we need to find, let's say C1. So I want to eliminate C2. So I'm gonna multiply everything times this guy. So I'm gonna multiply times ICK plus ICK, and then ICK over here. So when I add the two things, so I got 2 ICKC1, and these two cancel, equals f of k ICK plus GK, right? And then when I divide by 2ICK, so I need to leave C1 alone because that's what I want. So I get IFK CK plus GK, and I divide by 2ICK, and I divide here 2ICK. So what happened is that this I cancel with this I, this K cancel with this K, this C cancel with this C. So I get C1 equals f of K halves plus GK over 2ICK. Okay? Okay, so to find C2 now, well, I don't know if I would like to leave you this to do it for yourself, but well, let's do it. So you guys cannot complain that I didn't do the whole formula. So this is C1, right? So now I need to find C2. So for C2, so remember I have C1 plus C2 equals f of k. So C1 is all these guys, so I'm gonna replace it. F of k. So I'm just doing it so you guys don't feel afraid of these complex numbers. So algebra of these complex numbers equals to fk divided by 2. Yes, what am I doing? Sorry. Sorry. So this is C1 plus C2, and then equals to f of k. Now I move all these guys to the other side. So I move C2, I move the other guys, so I got minus fk halves plus fk, so I have fk halves plus gk 2ick. Okay? Uh-oh, I'm supposed to get minus. Oh yeah, minus, right? Because it moves to the other side. So I got C2 and I got C1. In conclusion, I had my solution. My solution looks the following way. My solution looks like, this is y of t, right? So y of t, I said this is y of t, right? But this is really ukt, right? I didn't want to make you feel scared with these two variables, but you don't worry about that. So my solution is UKT equals FK halves plus GK over 2ICK e to the ICKT plus FK halves, because this is C1, right? And this is C2. FK halves minus GK 2ICK and CK e to the minus ICKT. Okay. And then that's my UKT. So far now we are here in the third step. You see, this is my solution. So second step. So let me stop the here 31 minutes. Yeah. So let me stop here my video. So next part, on the next video, I'm gonna do the inverse Fourier of this part. So far until here, I haven't done anything very special. Just apply my formulas and solve an ordinary differential equation. The next part is requires some tricking. So going backwards is always a little bit trickier. So let me stop it here.